Every time a patient enters a hospital, they generate a massive, overwhelming stream of clinical, administrative, and financial information. Making sense of that information requires health data analytics, the science of examining raw data using statistical measurements to draw conclusions and find clinical trends. Once we identify those trends, we use health informatics. This is where we apply that statistical information to actually design better healthcare delivery systems and manage hospital networks. But to perform any of these analytics, we need aggregate data, combined information from thousands of individual health records. And raw clinical data is inherently messy, filled with unstructured text and overlapping medical synonyms. This flow diagram illustrates our ultimate target, translating raw data step by step into wisdom, pointing toward the triple aim. To the right are its three specific goals: improving patient care experience, reducing per capita cost, and improving overall population health. Reaching those endpoints requires a deliberate process of taking chaotic clinical inputs and forcing them into a rigid, standardized technical architecture. Before a single piece of data enters a computer system, its structural requirements and relationships have to be mapped out. The Entity Relationship Diagram, or ERD, acts as the architectural blueprint for these connections. These diagrams show how different entities interact. We can see a one-to-one relationship where a patient has exactly one attending physician, alongside a many-to-many relationship where patients share multiple consulting physicians. To fit neatly into these exact relationships, the raw data collected at the hospital must undergo normalization. Normalization breaks data elements down into the smallest desired detail. Here, an unnormalized address field is split into discrete fields for city, state, and zip. At the top, a combined name string separates into last name and first name to prevent system confusion. By enforcing this physical separation, we allow computers to accurately sort, filter, and search for specific data points across an entire hospital network. Once normalized, the data needs a place to live. Most healthcare organizations physically store this information using the relational database model. Data is stored in a strict grid. Each horizontal row represents a record for one specific patient. Each vertical column is a field recording the same type of information. To avoid confusion, a unique primary key, like patient ID, sets every entry apart. When this same primary key appears in a different table, such as a clinical encounter table, it acts as a foreign key. This establishes a strict mathematical link between the two datasets. Using this system of relational keys prevents massive data duplication. Since information is entered in only one place, any changes automatically reflect everywhere, maintaining single-source accuracy across the system. The relational model is highly efficient, but it has a major vulnerability. If a human types a date or an abbreviation inconsistently, the entire search function fails. Organizations use a data dictionary as a strict rulebook. The date of birth format rigidly requires a 2-digit month, 2-digit day, and 4-digit year. It limits every keystroke. A last name is restricted to exactly 25 alphabetic characters and nothing else. The information inside this dictionary is a form of metadata. Looking at this breakdown, we see the raw data on the left and the metadata on the right describing the exact data types and character limits. It is literally data about data. Metadata takes three forms: descriptive metadata, like the dictionary, structural metadata, like our relationship diagrams, and administrative metadata, which creates an audit trail by logging exactly who accessed the system and when. With these strict governance tools in place, designated personnel known as data stewards can perform data scrubbing, identifying formatting errors and fixing them to guarantee the integrity of the clinical information. Even with perfect formatting rules, medical language is difficult to database. Doctors use overlapping synonyms constantly, and a computer cannot instinctively tell that therapeutic and curative mean the exact same thing. To solve this, we use vocabulary standards. This block of text shows a raw, unstructured physician's note. Behind the scenes, a universal nomenclature called SNOMED-CT automatically interprets the clinical intent and assigns a unique numerical code for findings like dyspnea. Now that the data is standardized, normalized, and numerically coded, a database management system, or DBMS, takes over to control and manipulate it. The DBMS uses two main components: a data definition language to physically create and modify the tables, and a data manipulation language to retrieve and edit the information inside them. To execute that retrieval, we use structured query language, or SQL. A single SQL command can instantly search the entire network, filtering a massive database grid down to the exact rows requested. Translating chaotic human clinical notes into standardized nomenclatures is the vital final step required to make these complex, instantaneous SQL queries possible. We have built a complete operational pipeline. Raw clinical input is normalized into tables, governed by strict data dictionaries, and standardized by SNOMED CT. With this robust architecture in place, healthcare organizations can move beyond basic descriptive analytics, which only tell us what happened in the past. They can apply predictive analytics. By feeding this perfectly structured historical data into statistical models, they can forecast future events, such as a sudden spike in hospitalization rates. From there, they use prescriptive analytics to test that modeled data and generate highly specific, actionable operational strategies for the network to follow. Improving patient outcomes, controlling costs, and protecting population health are complex goals. Achieving them relies entirely on the uncompromising discipline of database architecture.